Welcome to the first part of the problem-solving session for Chapter 9. Let's begin with the first question. A jogger of 85 kilograms, let's call him number 1, is running with a velocity of 2 meters per second in the I-hat direction. Another jogger, let's call him number 2, a 55 kilogram mass is running at a velocity of 2.5 meters per second in the I-hat direction plus 1.6 meters per second in the J-hat direction. In other words, in a coordinate system and in an XY coordinate system, he might be running something like, here's X, here's Y. He might be running along, let's say, this direction here. So rather than just along the X direction as jogger 1 seems to be doing, and this might be east, for example, north, west, and south. So in other words, the street is actually a two-dimensional plane, and so not everything moves in either one specific direction, such as east, west, north, or south. All right. Well, we are asked to determine the total momentum of this system of joggers. So in other words, here the two joggers make up a system, and we're seeking to determine the momentum of this system. Now notice that we are very specific here about directions, the I-hat, the J-hat, and if we had the third dimension, the K-hat. That is because momentum is a vector quantity, and so it is no longer sufficient, as was the case in Chapter 7, Chapter 8, for example, to focus only on the speed portion. That is because in Chapter 7 and 8, we were dealing with scalars. Kinetic energy is a scalar quantity, potential energy is a scalar quantity, work is a scalar quantity. Here in this chapter, when we are expressing the quantities of momentum or impulse for that matter, we have to be very careful that they are vector quantities and we have to specify them fully. All right. Having said that, we want the total momentum of the system, which means we want an equal sign there. We want the momentum of the first jogger added to the momentum of the second jogger. Now we don't have an initial or final here. We're just told this is what it is and that is the way it stays. Tell us what the momentum is. All right, so M1 V1 plus M2 V2. All right, now M1 is 85 kilograms. V1 is 2 meters per second in the I-hat direction. M2 is 55 kilograms. And V2 is 2.5 meters per second in the I-hat direction plus 1.6 meters per second in the, let's put our J-hat direction there. All right, so now remember that when we have I-hats added with I-hats or J-hats added with J-hats, we can combine them. What we can't do is combine I-hats with J-hats. In other words, we cannot add I-hats with J-hats, but we can add similar unit vectors, like unit vectors. In the first term, we get 170 kilogram meters per second I-hat plus 137.5 kilogram meters per second I-hat plus 88 kilogram meters per second J-hat. Now these two terms are I-hat terms, and so it is perfectly all right to combine them. In fact, we should, because we want to reduce to the lowest term. Okay, let's take into account, sorry about that, three significant figures, 308, oh, we lost it again, kilogram meters per second I hat plus 88 kilogram meters per second J hat. Notice, by the way, that there is no abbreviation for the unit kilogram meters per second. It just simply is, and we're stuck writing it out whether we like it or not. In other words, we don't have a Newton or a joule or a watt that we can substitute to prevent having to write this product of units. All right, so that's the first question. Let's look at question number 2. Here, find the following using the force time curve, which is shown below for a baseball that is struck by a bat, and determine the impulse delivered by the bat and the average force exerted on the ball. So in other words, here the impulse is delivered by the bat, and that impulse is the force which is exerted on the ball over a certain time period. Now, the thing is this, when we define impulse, we defined it, we wrote it in 2 ways. We said impulse can be written as the integral of f dt, okay, it is a vector, but it can also be expressed as f average times delta t. All right, now what we have here in this graph is a curve of f, which is bounded by the horizontal axis. In other words, f grows from 0 to its maximum value 18,000 and then depreciates from 18,000 back to 0, and this occurs over a time frame of 1.5 millisecond, in other words, e to the minus 3 seconds. This force is not constant, okay, in time. It is not constant, which means that we can either obtain the average of this force or we can integrate the force over that time period to determine the impulse. Okay, well, to integrate this force is a little complicated. How about this? If we look at the area under this curve, which is bounded by the horizontal axis, there's the horizontal axis, that area is entirely equivalent to taking the integral of f dt, believe it or not. Okay, what is the area of this curve? Well, it is a triangle, and we know that the area of a triangle is 1/2 base times height. 1/2 base, 1.5 e to the minus 3 milliseconds, times the height, 18 e to the 3 newtons. Okay, put this all together, and that gives us 13.5 Newton seconds. And in fact, that is the impulse. So we have effectively determined the impulse, and let's just refer to the magnitude here, because in fact they did not tell us what the direction of this impulse is. So we magnitude wise at least know that the value is 13.5 Newton second. For the next part of this problem, they ask us to determine the average force. And again, we're going to just work with the magnitude. But look here. We are told that the integral of f dt is equal to the product of the average force times the increment of time. So, since we just determined the integral of f dt, which is our impulse, we can use that result divided by the delta t, which is, of course, that time period, 1.5 e to the minus 3 seconds. And this yields the result of, I believe it should be 9,000. Yes, in fact, 9,000 newtons. So on the average of this force was 9,000 newtons, but notice that, and so the average would be someplace along here, but notice that it was not a constant force, and therefore unless we knew the average, we could not use the 18,000 here because that certainly wouldn't be the average. We'd have to know the average to determine the impulse. Since we didn't have it, we used the area under the graph. So essentially, there are three ways to determine impulse. Doing the integral directly, knowing the average force, multiplying it by delta t, or obtaining the area under the graph. Okay, and so this comes from the definition of impulse. So we're a little too far ahead. Let's see where we are. Okay, next problem. Question 3 says, in a particular car crash, a car of 1,500 kilograms collides with a wall, and the collision lasts for 0.15 seconds. The initial and final velocities of the car are 15 meters per second in the negative I-hat direction initially, and 2.6 meters per second in the positive I-hat direction after the collision. We're asked to determine the impulse of the collision and the average force exerted on the car. Now, even though this is a collision, the system here is just simply the car. And because there is an external force that acts on the car, namely the wall, okay, the wall is the agent which supplies an impulse due to that external force that the wall, and we all know that that wall can exert a force on the car. We wouldn't want to drive into a wall. That is the impulse that we were going to calculate from the information that's given to us. Now, the definition of impulse says that impulse is determined by the integral of f dt, the average force times delta t, or the area of a graph. Under the graph, the area of a graph, in other words, the area under curve bounded by the horizontal. Okay, what is another way that we can calculate the impulse without using the definition of impulse? How about a relationship? Okay, the relationship very similar to the work kinetic energy theorem, and that is that yet another method for determining impulse is to look at the change of momentum that a system undergoes. What is the system here? The car. So we want to look at the change in the momentum of the car to determine the impulse that's caused by the collision. And again, this is only through a very special relationship similar to the work kinetic energy theorem. So the change in momentum is, of course, the final momentum, and V final, minus the initial momentum, and V initial. And we've been given these quantities, so this should be a very simple task for us indeed. All right, let's see. We have, let's factor out the m's so that we have to, we have a little bit less to write, 1,500 kilograms. V final is positive 2.6, and I'll go ahead and put my I hat here, meters per second. And V initial is minus 15 I hat, but we have a minus in front of the minus, turning this into a positive I hat meters per second. Well, let's see. Remember, we can combine I hats with I hats. Here, this yields 17.6 I hats, and when we multiply that by 1,500 kilograms, we get 26,400 kilograms meters per second in the I hat direction. That's the impulse that the wall delivers to the car, and that's quite an impulse. Now, the next question is, associated with this impulse, what is the force, average force, that the car experiences? Well, again, we go to the definition, because now that we have the impulse, it is not a difficult task at all to determine the average force. And remember, they told us the contact time between the of the collision. In other words, the car in contact with the wall. 26,400 kilogram meters per second divided by the time of contact. They told us that was 0.15 seconds is our average force. And here I can keep the vector nature because, of course, I have been told what precisely the direction of the quantities related to the momentum were, namely the I hat direction. All right, so F average works out to be 176,000 newtons in the I hat direction. So I have effectively determined the force that the wall delivered to the car. Let's write this: force of wall on car. How about let's throw the following question: what is the force of car on wall? Remember Newton's third law? What did Newton's third law tell us? It guarantees us that action-reaction means that the force that one object exerts on another is equal in magnitude to, to get this back again, to the force that the other exerts. However, it is in the opposite direction. So force of car on wall, force of wall on car. And how did we know that this was the force of the wall on car? Because this came directly from impulse. And after all, we asked, what is the impulse that the wall delivers on the car? Okay, let's go to our last problem in this part. Question 4. A neutron in a nuclear reactor has a mass of 1.675 e to the minus 27 kilograms. And here, what we're going to do is we're going to call the neutron, m sub n, let's call it object number 1, just to make our life easy. It also has a kinetic energy of 1.595 e to the minus 13 joules. And again, this is the neutron. Okay, so this is the kinetic energy of the neutron initially. It makes an elastic collision. Now, notice this is a very important term here because it's describing the type of collision that this neutron is going to have, and therefore telling us what two quantities are conserved in any elastic collision. Answer: momentum and kinetic energy. And so we have to keep that in mind, that both of these are conserved. All right, so the collision is with the nucleus of a carbon atom, and the carbon atom, they're telling us, is 12 times the mass of the neutron. They're also telling us that the carbon atom is initially at rest. They want us to determine the final kinetic energies of both the neutron and the carbon. Now, if we are solving for two quantities, K, I apologize that I have that E there, but it's K1F and K2F. Those are two unknowns. Two unknowns require two equations, okay? More than that, we see that because of the nature of that collision, we have the combined conservations of momentum and kinetic energy in the following equations. A very long equation, if you recall back from the notes, for applicable for elastic collisions and have to be used. V1 final equals M1 minus M2 over the sum M1 plus M2, V1 initial plus 2M2 over M1 plus M2, V2 initial. So this is going to give us one of the unknowns. Now, we also know that V2 initial is equal to 0 because remember, object number 2 is our carbon atom and it was initially not moving. So we eliminate at least that term. There is a second equation for determining the final velocity of the second object, again the carbon, and that is 2m1 divided by m1 plus m2, v1 initial, and just for the sake of writing it, the next term m2 minus m1 over m1 plus m2, v2 initial, and boy, I love to do this, set it equal to 0. All right, so let's substitute in our values. And we're going to try to make life as easy as possible for us. Write all masses in terms of m1. m1 minus 12m1. Remember, m2 is 12m1 divided by 13m1. That is m1 plus 12m1 times v1 initial. We can combine the m1 minus 12m1 to end up with minus 11/13. The m's are going to cancel. Look at this. Works very much in our favor. v1 initial. And from here, v2 final equals, let's see, 2 times m1, 2m1 divided by 13m1, m's cancel, oh, and all this, of course, times v1 initial, let's not forget that, gives us 2/13 v1 initial. Okay, now, this is all fine and good, but how do we get v1 initial? Well, come back up here. Look, they told us that K1 initial, remember the neutron is object number 1, was 1.595 e to the minus 13 joules. And don't forget that kinetic energy has the form 1/2 m1 v1, in this case initial, squared. So if we want v1 initial, we are going to have to use the value of the kinetic energy and work out this number for ourselves. Okay, now let's write some things down. So we've got v1 initial equals, well, let's keep it squared first. It's going to be 2 times K1 initial divided by M1. We'll take a square root and plug in the numbers. 2 times 1.595 e to the minus 13 joules divided by 1.675 e to the minus 27 kilograms take a square root, and we get 1.38 e to the 7 meters per second. Now we can plug this into here, plug that into there, and get the actual values of V1 final as negative 1.17. And by the way, direction-wise, let's go ahead and have the I hat direction as the direction that the neutron, or object number 1, was initially moving. So what we see here is that the neutron is going to bounce back after the collision. It makes a head-on collision with the carbon atom. The carbon atom is 12 times more massive. And so this poor neutron is going to rebound and bounce backward in the minus I hat direction. Now, the carbon atom, whereas initially was not moving, this carbon atom is now going to experience a velocity of 2.12 e to the 6 meters per second in the positive I hat. So it won't be moving as fast as the neutron, but it will have been set into motion. Now, to get the kinetic energies, I'll just write down the terms because I actually did not work it out with a calculator, but I trust that you should have no trouble getting these terms. 1/2 m1, the mass of the neutron, times minus 1.17 e to the 7 meters per second. Let's put our little I hat here, squared. Now, what is I hat, dotted I hat? It's 1. And so that converts this vector quantity of V1 final into a scalar, V1 final squared. Okay, because there will no longer be an I hat term. And so you can get that value. K2 final will be 1/2 m2, or 12 times m1, times 2.12 e to the 6 meters per second I hat, square that, which again, I hat dot I hat is 1, and that should give us a number. Well, this concludes the first part of the problem-solving sessions for Chapter 9. Until next time.